So, hello. Today we will talk about transaction isolation and concurrency control in Postgres. My name is Khonski. I'm a Wriker. I started my career in 2012. I worked in different companies, outsourcing companies, startups, corporations, and now I work in Wrike. I'm a backend reliability engineer, and myself and my team, we are working on a variety of problems. First, we scale Wrike. We currently have 2 million users, and we want to double that amount. So we want our infrastructure and services to be able to handle the load. We resolve production incidents. We add alerts monitoring to make sure that we know what is going on in our system. We also work on performance improvements. So about Wrike. Wrike is the best collaboration tool in the world. It is used for task management. It gives you transparency and visibility to your project, so you know which project is dependent on another project. It shows you blockers, dependencies. We have Gantt chart feature, so you can see all your tasks, their timeline, schedule, and who is blocking who. You can see users assigned to the tasks. So it's like Jira, but better. And we are used by different organizations, not only by IT, but also by sales, marketing, and so on. We have a large scale of customers. We have, for example, Google, Airbnb, Siemens. We also have small customers like businesses with 10 people. We have a lot of there are more than 1,100 people around the world working with Wrike, for Wrike. So yeah, we're quite a big company, yet not as a big corporation. So today's agenda. We'll take a look at transaction isolation. We'll recall them, what they are, what the trade-offs between them, and then we will formulate the problem. In the second part, we'll talk about concurrency control. We'll recall optimistic and pessimistic concurrency control, and then we will dive into multi-version concurrency control. And at the end, we'll talk about vacuum. So a database is a collection of data stored and accessed electronically. There are a lot of different databases, such as key value pairs, relational. Then we have graph databases, and so on. A database management system allows users to access the data, define it, create and maintain control. Who can update the data? Who can access it? And there are other things such as backups, recovery, and so on. So you remember ACID properties from the relational databases. Like most databases have them, but we'll talk. So it's atomicity, consistency, isolation, and durability. However, not all the databases are ACID compliant. For example, Amazon DynamoDB. Before 2018, it was created as eventual consistent data store. Amazon had a specific problem. A user buys an item and the right operation should be always available. In Amazon case, if a user buys an item and some network failure happens, it's better for Amazon to have user with 2 items than with 0 items. And later they implemented actually transactions, but with some limitations. First, it allows to have total memory of 4 megabytes for transaction. And second, in Amazon DynamoDB, write transactions have serializable isolation level, and read transactions have read committed level. We'll talk about that. So MongoDB, another example. Before version 4, Mongo did not allow to have multi-document transactions, which means that you couldn't update multiple documents atomically. So what is concurrency? It's ability of a program to change the order of different parts while still get the same outcome. It's a precondition to parallelism. So let me show you a picture. We have a set of instructions A and instructions B. We can reschedule them while still get the same result. And we then can execute them in parallel. So what is today's problem? We have multiple users that read and write the same data. One solution that is used no concurrency. Originally, in 1981 and in these years, the amount of load was not as in today's world. And you could execute, databases could execute those transactions in sequential order. And the reason is because they had, as this article says, 10,000 terminals with 100 active transactions at any instant. So the load wasn't huge. You could execute those transactions sequentially, and there were no problems. Another solution, Redis. As you know, Redis has a queue of events where incoming requests come, and then there is a worker thread that takes those events and processes them one by one. As a result, you don't have to worry about logs or contention because you either read or write. You don't do it in both at the same time. Of course, you can use a partitioning of Redis. You can run multiple instances of Redis on the same CPU, but those Redises will have their own memory, their own data. Thus, there is no conflict. So we'll talk about transaction isolation. It describes the degree how other concurrent transactions can affect each other, and what kind of anomalies or side effects can be accounted during the execution. Achieving consistent isolation comes at a cost, because we need to have more logs, we need to consider synchronizing those effects, and this will reduce the performance. SQL standard defines 4 levels of transaction isolation. The most strict is serializable, which defines that if you have a set of concurrent transactions, you execute them concurrently and get some result as if you run those transactions in some sequential order. So the order doesn't matter. The thing that matters is that the order exists in which you can get the same result. So we want to understand how can we achieve this result. So a database has a schedule. A schedule is a list of all operations from the transactions that we are currently executing on the database perspective. So those transactions that read or write the database. A complete schedule, it contains all operations from all the transactions that we are executing in. A serial schedule, so we want to run those transactions independently. We first commit one transaction and then start a new transaction. It will affect the performance, but for us it will be easier to understand such schedule. And serializable schedule, it is equivalent to some complete and serial schedule over the same set of transactions. Let me show you an example. We have 2 transactions, T1 and T2. They have operations. And if we reorder those operations, we can first execute transaction 1 and then transaction 2, or we can execute transaction 2 and then transaction 1. So we will get some result, and these are 2 examples of serializable schedule. In SQL, there are defines phenomena, and on those phenomena you can define transaction isolation level. Or, in other words, you choose that transaction isolation level that you want to avoid some anomalies. So one of the anomalies is dirty read. It happens when a transaction reads data that was modified by another transaction, but another transaction hasn't committed it. So let me show you a picture. We have 2 transactions running. First, we have actual data, some task in the database. Transaction 1 starts, it updates the data, and the data is immediately written to the store. And then we start the second transaction, and it reads the data just that was written, but the first transaction hasn't committed. So what happens if the transaction 1 rolls back? It means that transaction 2 read data that should not exist in the database. So this is an example of dirty read. Non-repeatable read. It happens when we first execute the select query, we get some result, and then we execute the same query with the same condition, and we see that our result has changed because there was another transaction that updated the value. So, example, transaction 1 starts, it tries to update something, but it hasn't committed. We run the second transaction, it selects data from the database, then transaction 1 commits, and we re-execute the same query. And now we find out that the value has changed. So this phenomena is called non-repeatable read. And as you see, transaction 1 has affected transaction 2. A phantom read happens when you have a range of records, you execute a query against them, you get the result, but another transaction has changed the rows. For example, it inserted more rows or deleted some rows, and when you re-execute the same query, you get different result set. So, an example, you have some rows in the database, you start transaction, you insert new records, but you haven't committed that transaction. You start another transaction, you try to read something, you get the result set. And then the first transaction commits. And then you repeat the same query. And now you get different result set. So this is phantom read. Serialization anomaly. It happens when you have a group of transactions, run them concurrently, and you get some result. If you execute those transactions in any order, you will but sequentially, you will never get the same result. I will show you an example. Also, you can find some tutorials, and they say that write skew, and the write skew is also an example of serialization anomaly. So you have some data in the table, you have some, and you start execute transaction 1. You select some of records where class is 1, and you get some result, which is 30 in our case. You start another transaction, you execute some for class 2, and you get value 300. Now you try to insert in the first transaction the value with 30 that you read before, and commit. And then later you insert value in the second transaction that you read also before, and commit. Now you will get result set. But what happens if you run these transactions one after another, sequentially? You will never get this result. So let me show you an example. If you run first transaction 1 and then transaction 2, the last inserted values are 2, 30, 1, 330. If you change the order of those transactions, the result will be 1, 300 and 2, 330. What we received was 230 and 1, 300. So this is a write skew. There is also dirty write, but in modern databases it doesn't happen. But it's when one transaction is writing something, and then another transaction is writing something, and then the first transaction is rolled back. But in modern databases it doesn't happen. Read skew also happens when you have some constraint, some rule. You try to execute one transaction, you select value, then you run another transaction, it updates something, it commits, and then you continue with the first transaction reading another value. And now you have violated your constraint. So this is read skew. And lost update. It happens when you have let's say several transactions. One transaction tries to update something, and another transaction modifies your data. And the result is that the update operation of another transaction was lost. So again, two transactions. First transaction tries to read data. Another transaction starts, it updates something, commits, and then you commit in the first transaction, because imagine you retrieve some data, you want to update, and then update it. And as a result, now the write operation of the second transaction was lost. No one has ever seen it. And in Postgres, there could be read uncommitted is not like, let's say that it works the same way as read committed in Postgres due to its implementation. So in read committed, dirty read is not possible, but all other anomalies are possible. Non-repeatable read isolation level does not allow dirty read and does not allow non-repeatable read. Also in Postgres, it doesn't allow phantom reads. And serializable isolation level does not allow all these anomalies. Also, if we add those read skew and lost update, you will see that they were possible only for read committed. For other transaction isolation levels, those anomalies are not allowed. So which isolation level to use? So you want to, by default, it's read committed. It's a good compromise between performance and data consistency, like transaction, like anomalies you can encounter. So it performs well, but there is a catch. How do you test the code that if there is data inconsistency? If you, for example, read something that was changed, so it's hard to reproduce such errors, but they can happen. You should expect. On the other side, repeatable read eliminates some anomalies, but not all of them. Now, as a developer, you have to modify your code to handle serialization failures. For example, you try to read something as repeatable read and someone else modifies it. And then you try it in the first transaction update it. So your first transaction will be aborted, you have to retry it. So you have to write such code. It's a drawback, but non-repeatable read could be used when you want to have, for example, report. You want your report to be valid at some moment of time. So you start the transaction and you can say that at the start of the transaction all the data was like it was in the report. And the serializable isolation level, it's the most strict. You don't have to worry about the consistency errors, but you have to write the logic that will retry the transaction because there'll be lots of conflicts and you have to deal with aborted transactions. And they also affect the performance. You could use serializable isolation level if you know that your data set is large and you know that probability of different transactions modifying the same row is very low. Then you can use serializable isolation level. Also keep in mind that when you run transactions in the serializable level, it's not supported on replicas and it cannot be combined with other isolation levels. This is for version 14. Now the second part, how do we achieve it in our database? So we'll look at logs and multi-version model. So what is concurrency control? It's a mechanism that maintains atomicity and isolation. There are a set of techniques for handling interactions between concurrently executing transactions. There could be optimistic concurrency control, pessimistic concurrency control. For example, we'll look at two-phase locking and multi-version concurrency control. And all these approaches have different flavors or variations. Optimistic concurrency control, you expect that read and write operations do not conflict, so if a conflict happens, you have to abort one transaction. And you expect that conflicts very seldom happen, so this model can work. Pessimistic concurrency control can be locked-based and without locking. In locked-based approach, there'll be locks that prevent other transactions to update or read the same data that another transaction is modifying. In non-blocking approach, you have to maintain list of read and write operations and restrict them based on the schedule of unfinished transactions. So lock. Let's say that there are exclusive locks and shared locks. Shared locks used for reading and exclusive locks used for writing. In the database, you know that there is a row, then there is a page that contains rows, and then there is the whole table that can have multiple pages. And imagine that you try to take logs for several rows. Once there are too many rows in your page, it will be easier for the system to maintain single log on the whole page instead of holding logs on individual rows. Once you need more pages, the database will decide that now it's easier to maintain the whole log on the whole table. So this is an example of multiple granularity logging. So log has a structure like hierarchical structure that it has a node and then child node also can contain. And also originally those isolation levels and especially serializability could be achieved with two-phase locking. It was proven a long time ago. And this approach consists of two phases, expanding phase and shrinking phase. Once you start expanding phase, your transaction will try to acquire all the logs that it needs. After that, it will perform it will execute its actions and then it will start releasing the logs. If your transaction has acquired any log, and if it cannot acquire any log, it will have to release all of logs that it has. And if your transaction released the log, it cannot acquire new logs. And initially, all the databases employed this protocol. So in Postgres, for example, you can use select for update or select for share, and it will implicitly say that, okay, now hold the lock on the record because I want to modify it later and don't allow other transactions to do anything with that. So you select for update in the first transaction, then you start a second transaction. It tries to modify the record, but it cannot because it has to wait until the lock is released. Now you update your record in the first transaction. The second transaction is still waiting because there is a lock. But once you commit your first transaction, the second transaction lock is released, so it can continue. Maybe it will find the conflict and it will retry, depends. But it will continue only after the lock is released. So I will show you some example we had long time ago in some company. It was unpleasant, but we used the MS SQL server. We had the read committed transaction isolation level, and we found out that SQL server uses shared logs to prevent other transactions from modifying the record. We received this exception. It says timeout. We couldn't acquire connection, so we started looking into. There was a code, yeah, it was more complex than this, but the idea was that some guys wrote that transactional annotation on a very big piece of code. So what happened here? We used cache, caffeine library. Caffeine library under the hood uses concurrent hash map. So here we had one thread that tried to call database, update some record, and then it wanted to update the cache. So it updated the record successfully, the database transaction was still open, and then the thread went to hash, to modify, to update the cache value. But when it came to the cache, it has to wait for the lock, because concurrent hash map uses locks on buckets. Because another thread took that lock, because we use read-through strategy, so another thread went to cache, tried to read the data, it didn't find it, so it was cache miss. So that thread says, okay, now we need to get data from the database. It started another transaction, read transaction, that tried to read exactly the same row that the first transaction updated. But it couldn't, because the row was locked. So it was very unpleasant. We had to analyze the thread dumps. How did we fix it? The quick fix was we enabled snapshot isolation level in MS SQL server, and the proper fix was we had to change the logic in the code. So rules of thumbs. Transactions or transactional annotation should be in your code only on DB changes. If you want to update the cache, do it after your transaction is committed. If you want to modify database record and send message to the message broker or Kafka or whatever you want, you can consider outbox pattern or other approaches, so you don't want to write such code in a database transaction. And the most important, it's good for you to have some understanding how your technology works internally. So, multi-version concurrency control. As we saw that we needed logs to make sure that there is no conflicts, and those logs could make transactions wait for each other, and long running transactions could slow down the whole system. So people started looking for an alternative. MVCC promises that readers would not block writers and writers would not block readers. The only problem could happen if there are two writers modifying the same data. So in this case, one transaction will be rolled back. And in Postgres, they started with a snapshot isolation. It's the idea is that for each transaction, you have a snapshot of your data that is that represents data at particular moment of time. So snapshot isolation minimizes the number of logs that required, and Postgres uses multi-version flavor of snapshot isolation. And the idea is that at any moment of time, there could be multiple versions of the same row. So let's take a look how Postgres implements it. If you read source code, of course, Postgres is being developed, it can change. But I'll try to give you some simple picture of it. So it has xmin, xmax, cmin, cmax, and ctid. It also has some other flags, and it has user data. So xmin is ID of the transaction that created the tuple. Xmax holds the ID of the transaction that deleted or updated the tuple. Cmin contains identifier or command ID that inserted this row. Cmax is the command that deleted the row or zero. And the ctid is physical location of the row of within its table. Of course, ctid will change when you run vacuum full or when someone updates the row. So you shouldn't rely on it in your code, but it's good to understand what's going on inside. So, what is a snapshot? Every table and index is stored in files, and those files have pages. A page is written in the buffer and then it's flashed back on the disk. And the page size is usually 8 kilobytes. So a data page can contain several versions of the same row. And also sometimes you can have rows and different versions can be stored in different pages. So the thing is that each transaction can only see one version of the row at most. It cannot see more than one version. And to ensure this, how we achieve it? Each transaction has its own snapshot. And all rows that currently accessible, that your transaction is readed, all those rows contribute a snapshot. And the snapshot sees the data that was taken by previous transactions that committed. So now there is a catch. Imagine you have multiple rows in the database, multiple transactions that are trying to read them, and do you want to make physical copies of those rows? It will be very difficult. It will be hard for I/O, for disk, right? And it will be slow. So guys from Postgres came with a different idea. So a snapshot is a data structure. It has a xmin field, which is the lowest boundary of the oldest active transaction. Then it has xmax field, that is the upper boundary, that is ID of transaction that exceeds the latest committed transaction. So it defines the moment when the snapshot was taken. And we also need the list of transactions in progress that were running at the moment when we created the snapshot. So This information will help us to like the database to understand which version of the row a transaction can access at some moment. So those rules, like how do we check if transaction can access this version of row or not, are quite big and complex. Again, you can check the source code if you want, or you can Google it. They have some simplification. So you create a snapshot at some moment of time. Transactions that committed before that time, their changes are visible in that snapshot. However, transactions that started before you created snapshot and haven't committed yet, or transactions that started after the snapshot, their changes are not visible in that snapshot. So this is a very simple explanation of those rules, but they are much more complex. And of course, we need transaction ID. So when we start a transaction, when you try to update something, then the transaction is given transaction ID. It is a 32-bit integer. And here we have a problem. Like 32-bit integer, it means that there is limited number of those transaction IDs. And what happens when you run out of them? So the idea is that 2 billion of transactions are to be considered as future transactions, and other 2 billion of transactions are considered as past transactions. And when we want to define if a row is visible for that snapshot or not, we want to understand if it was created in the future or will be created in the future or in the past. So what we can do, we can run periodic vacuums, because what vacuum does is that it checks if the row created a long time ago, like more than 2 billion transactions before, then it will mark that row as frozen. And therefore, the visibility logic will check if the row is frozen, then it means that it was created in the past, but not in the future. So this is how Postgres solves this problem. I oversimplified it because it's a little bit more complex. So let me show you an example. So we have 2 transactions and we run them in read committed isolation level. We have some data. I will show you how we got this data. So we try to select the record, and we also try to select those fields like xmin, xmax, also physical location, and the current transaction ID. And what we have is that current transaction ID ends with 115, and the record was created before in 113th transaction. And another transaction also selects the record, and we see that it's same record, same physical location. It has same xmin because they create its same record, but the current transaction ID is different, maybe because it started before, so it has 114. So now the first transaction updates the data and commits it. And the second transaction tries to select it again. So what we will see is that xmin now has the ID of the transaction that committed. So it means that it's a new version. It was created by the first transaction. And also you see that it has different physical location. While the current transaction ID is the same second transaction. Now, what would be different if we run the second transaction in repeatable read mode? The result would be that when the second select would return the same data as it was in the first select, but the xmax field would be 116. I mean the next transaction. So that's the only difference. So 2 differences. You get data same as you read before, but xmax would be set to the future transaction. So it means that all future transactions, like 116, so all future transactions will not see this version of the row. Now, of course, here is a problem. When you create for each update a separate version of the row, your database size is starting to grow. Also, when you perform searches on such databases, They will take longer because you will have to check more records. Also, you have indices in your database, and when you create a new version of the row, your index still points to the old version of the row, because otherwise you will also have to update indices, which is also from performance not good. And the index points out to the previous version, and the previous version has X max, which means that the identifier of the latest version of the row. So now you have to clean your database, and Postgres provides vacuum operation. What it does, first it eliminates outdated tuples, and also it freezes rows, which means that resolves this problem with ID wrap around. And vacuum can run in parallel with production database operations. So in theory, vacuum, when you run it, it should not block your read or write operations. But in practice, it's slightly different. It can affect performance. We'll take a look. Also, there is a full vacuum. Full vacuum reclaims disk space, more disk space, but it runs more slowly. And also, full vacuum needs exclusive lock for the whole table. So in this case, you cannot do anything with this table until full vacuum finishes. So how it is done? So vacuum consists of steps. First, there is a visibility map that has a track of, because again, you have pages. Those pages contain tuples, and you are interested in cleaning pages that have all the tuples outdated. So you do not touch pages that have valid data. So you start heap scan. What it does, it checks the visibility map. It skips all the pages that contain data that cannot be removed, and it populates an array of TID with tuples that you want to remove, that vacuum will remove. The second step is index scan. The problem is that if you have a tuple in the database, you cannot point from it to the index. It's the other way. Of course, Postgres have some modification for B-tree indices, but in general, you want to go from index to the tuple. So this step checks the index, it checks references to the outdated tuples, and cleans the index. After that, the step goes heap vacuuming. So now you can remove the tuples that are in TID array. And when you remove tuples from the pages, this space is not reclaimed back to your system. Instead, it could be used for new tuples in the future. But sometimes you also can have heap truncation. It's the last step. When you clean up pages, you can have empty pages at the end. Those pages you can remove. But in this case, this operation will require a short exclusive lock for the table. So you will remove empty pages. And in Postgres, you usually have after vacuum, which is a periodic job. It has lots of parameters. It checks fill factor, like how many dead tuples are there before you start executing. Also, if you change your data frequently, those operations could run also frequently. I don't have a picture, but what we had, that once we had a vacuum running on our database, it affected the performance. So yeah, our service had increased latency. Sometimes we use also replicas, so sometimes we could forward our traffic to those replicas. Those are read replicas. We use logical replication, but sometimes, yeah, that could be a problem. Fortunately, we deal with that. So what is the most important from today's talk is if you want to build for scale, if you want to build product that is used on the global level, you want to have millions of users, it's good for you to have understanding how your technology is going to work internally, at least to some extent. It will help you to make trade-offs, to consider other alternatives, because once you start running full production, the cost of migrations and changes will be much higher. Also, If you want to learn and participate in this, if you want to build world-scale applications, if you want to learn how to monitor them, how to build them, or just contribute, you can consider Wrike as your next career step. And that's all. Now you can go and watch your databases. So thank you. You can also read about us. And I also provided list of some research notes and documents you can read. There is also a book about Postgres internals if it's interesting for you. So I will answer questions. If some questions are big or require some discussion, then I will probably answer them later. I will watch recording of this video, and in comments I will also answer. So now I can accept some questions. Yes, reads also should be blocked during full vacuum, because full vacuum takes exclusive lock for the table. Exclusive lock means that no one else can access the data. So next question, please. How do we deal with auto vacuum affecting performance? Yeah, that's a very challenging thing. As I said earlier, we use different things, like we use circuit breaker, we use also replica. So if you see that the request didn't, we tried to execute a query and the response didn't come within certain amount of time, we start sending traffic to the replica or just wait. So usually, yeah, sometimes for some critical tables, performance could be affected. Also, what we consider other options, like having table partitions, like splitting big tables into smaller, so only small part of the data could be affected. Also, we use sharding. Sharding means that we have a lot of data and the data doesn't fit the physical cluster, so we have clusters around the world, and it means that if you run vacuum operation, the blast radius is small. Only customers on specific shards are affected for a short period of time. So this is how we deal with it. It's not perfect, but we are still researching how to do it better. So do we have centralized DB for all customers? So I could answer this question to some extent. So for each we have shard which contain customer specific data, and those shards are different. So we have a lot of shards. Each shard can contain different customer data. Also, sometimes we have to move, let's say, active customers and more passive customers together, so to balance the load. And of course, we host it. It's Wrike is a software as a service platform, so customers do not host anything. It's us to provide the service for them. And if we have some centralized database for customers, let's say that we have one common databases where we keep some very things that, let's say that, for example, when we have a request, we want to know where to forward, to which shard. So we have like a database where we want to quickly find out who is going to process that request. And yet we are also scaling it, so splitting it. So how Postgres keeps up with high concurrent load produced by non-blocking programming? So I would be honest, I haven't done it myself, but what can I assume, that it actually doesn't matter whether your programming is non-blocking or blocking, because you have, let's say that in Postgres you have incoming requests coming, and then Postgres has a number of connections. Right? Each connection is a process. And then once a request comes to Postgres, Postgres will create plan, then will execute the query. And Postgres has limited number of those connections. What it means that your program, a client, will have to wait until a connection becomes available. We have connection pool, request, so your application takes a connection from the connection pool, it goes to proxy, we use PG bouncer, then it goes to Postgres, and if there are all connections are taken, your program will have to wait. And if you use non-blocking programming, it means that there'll be some context switching. So the original request will be waiting until the database responds. This is how I understand the non-blocking programming. But once database responds, this virtual thread, or how it's called, non-blocking thing, will continue executing its request. What isolation levels should do use in Wrike? Mostly we use default level, which is read committed. For some cases we use different, but like for most operations, like for all reads we use read committed, and for updates we usually use read committed. So yeah, read committed. What isolation level should I choose for R2DBC, reactive communication with Postgres? Again, I haven't worked with reactive, or I worked with asynchronous programming, but not with a database. So here you probably should ask someone who has done it before. I won't be able to answer. And next. What are you thinking about microstream in comparison to databases? Yeah, I would not comment much because I heard about I talked to those guys. To me, I'm more like old traditional guy. I use things that have proven in the production databases that were used by different companies. Microstream maybe solved the problem. I don't know, I haven't used, but I don't want to comment. Also, as I mentioned before choosing technology, it's better for you to understand how it works internally. For example, in 2016, if you read the document, there was Uber and they used Postgres, and they migrated to MySQL. They complained about performance, they complained about some issues with replication, some bugs. Of course, guys from Postgres fixed some issues. So it would be ideal for you to use something that proved in production and then see if it works for you. Of course, if you are a small company, you can try using cool technology, but I wouldn't do that myself. If I build a startup, I would use something that has proven in the production. So thank you.